So we start again. And here, as I told you, for these azimuthal modes, you have this combination of these two modes. One is rotating in the positive theta direction. The other one is rotating in the negative theta direction. And it's a combination of these two which takes place. And for A is equal to B, for example, you have a combination which gives you cosine and theta, and it corresponds to a standing mode. And if you take, for example, B is equal to 0, A something, then you have a rotating mode which rotates in the positive theta direction. If A is equal to 0 and B is equal to 1, it's the other way. So you have spinning modes which can rotate in one direction, in the other direction. You can have standing modes which are formed by the combination of these two. And you have also intermediate possibilities. That's why we call that degenerate, because you have various possibilities for the same eigenfrequency. The eigenfrequency is the resonant frequency here. So this is shown here. This is, for example, a mode which is standing in this, I just represented the structure of this mode at two instants which are separated by half a period. So here you see the nodal line is horizontal, and you see that the red is at the bottom, the blue is at the top, and then the red is at the top and the blue is at the bottom. What happens when you have also longitudinal modes? You may have actually a combination. This is when you have also something in the transverse, in the longitudinal direction, so psi-m. And let's assume that this is open and this is closed. Why? Because we have an experiment which is just like that. And cosine kmz, the km's are given by this expression here. So the fm's are given by that. And when you have a mixed mode, it's in fact, just the sum of these two squared, and you take the root of that, the 1/2 exponent here. So for example, f11, so the first azimuthal mode and the first longitudinal mode is given by c over p square plus c over 4l square. And so f10, which is longitudinal, would be just given by c over 4l. This is the standard quarter wave mode. And here you have a combination of this mode plus the azimuthal one. And one has to take into account the speed of sound. What we've done, you can play with that expression, and we found in the annular chamber that we have, it's a slightly different configuration, and we actually used two speeds of sound. One which was close to the backplane to describe the azimuthal part of it, and the other one which is more characterizing the longitudinal part, which is different from that one. And by doing that, you can actually get some very good estimates of the frequencies. We will see that in a minute. In fact, the difference here is that the chamber that we are using has a plenum, and it has an outer wall which goes to this point, and an inner wall which is smaller than the outer wall. As a consequence, you have here a shear layer, and you have to take into account this configuration. In the center, you have a cold flow. The chamber is right here, and the plenum is here, and it's connected by injectors here. So if you want to do a calculation of the modes using a Helmholtz solver, in fact, you have to account also for what goes on inside in this place here, because it's part of the domain, because you see the two walls are at different levels. And here we do a calculation of the modes. So we get the first longitudinal 0 azimuthal, 280 hertz. This is 250 experimentally. The 2L 0A, A means azimuthal, so this is 470, and the 1L, 1A is around 769 numerical and 792 hertz calculated. One difficulty is that you have to account for the for this special exhaust here, so it's not quite. So you see it's not perfect. You don't get a perfect match between the calculations and the experiments. You can get the perfect match by doing this approximate expressions that I showed before. So we've seen the eigenmodes in such annular configurations. It's a good start to now look at what happens in annular systems. So this was just to prepare what we will now do here. And what we do is to study the dynamics of a complete configuration with multiple injectors. Actually, we have here 16 injectors. They're all swirled, but you can also replace those injectors by matrix injectors. And the walls of this combustor are made of quartz. And like that, you can watch the flame inside this device. So this is just a repeat of how you calculate the modes. We've just run through these slides. And now we want to look at these dynamics of these annular systems. Now, what we do here for annular systems is quite parallel to what could be done for example, rocket engines in cylindrical situations. Slightly more complicated. In the rocket case, you have more injectors. They are different. You are at high pressure. It's supercritical. We have also studies of that in the lab. So these are used in jet engines. This is the A380 here, has these engines, these very large engines. This is the CFM56. You have an annular combustor. So you find annular combustors in all these devices. And because the diameter is the largest dimension, these modes occur at the lowest frequency. So azimuthal modes are important because they correspond to the low frequency, and the low frequency is where the flames are more susceptible to perturbations. So it raises scientific problems and, of course, technical issues. So we need multiple injectors. So we want to characterize instabilities in these systems and examine what happens also. There is, you see, at first we started with swirling injectors, but already we've seen that swirling flames have a complicated transfer function. So then we had the idea, in fact, Daniel Durox thought that it would be fine to also replace all these swirler injectors by perforated plate injectors, because we have experience with these perforated plates. What is the advantage? The advantage is that the flames are laminar, and so you eliminate the complexity of turbulence. It's nice to have something which is simpler, because we have already other complexities here. So we did a lot of experiments with matrix injectors, perforated plate injectors. Now, what was the situation in this field? On single injector systems, a lot of theory, simulations, experiments, large number of investigations. On annular systems, a lot of theory. People have done theoretical work on configurations which are annular. So it's relatively large, of course, much slower than this. In terms of simulation, a few recent simulations of these configurations are available, especially by the group of Thierry Poinceau. They have had the courage to take a full combustor and look at what what goes on in something which is as complex as a real combustor. This is time consuming because you need a very large gridding. And in terms of experiments, very few model scale experiments. Of course, there are experiments in industry, but usually you cannot look at the flame, or you have just a few pressure sensors. It's very difficult to carry experiments in industrial systems, especially annular industry. Even 1 hour of operation will cost an enormous amount of money. I don't know how much, but very, very much. A big factor with respect to small scale. And then you cannot, you have to, everything relies on teams, on many people. And so we decided to have a small scale experiment. Not too small, but not too large. And this is the device that we designed. And how does that compare to what you find in the engine? This is annular, multiple swirling injectors, two-phase, kerosene, air, high pressure. This one is annular, multiple swirling injectors, premixed propane air. Propane is closer to kerosene than methane, so we decided to use propane. Atmospheric pressure, so of course this immediately you say, oh, it's not realistic because you are at atmosphere. But first of all, if you do atmospheric pressure, it's so much easier. So afterwards, if you have money, you can bring that to high pressure. And this is how the device looks like. So you have all these injectors, 16 injectors here. Yes, by the way, there is another experiment. I will show that later. It was developed in Cambridge by Jim Dawson and Nick Worth. We discovered that incidentally. We didn't know that they were doing an experiment of that kind, and I don't know if they knew that we were doing one like that. Their experiment is, our experiment is 40 centimeters here. So it's a reasonable diameter. The diameter has to be sufficient so that you get in the right range of, it looks somewhat like a helicopter combustor. Also, our swirlers produce a swirl number of 0.6, 0.7. This is typical. This is a measured swirl number. This is typical of industrial systems. Also, the plenum that is at the back here is more is closer to what you see in practice. So. But the main difference is that the swirl number is a reasonable one, while in their experiment it's pretty low, and they have a bluff body, in fact, in the injectors, while we don't. We have and so our case is somewhat closer to industrial systems. However, they are able to put more or less number of injectors. The spacing can be changed in their experiment. So they have experiments with 18 injectors and experiments with 12 injectors. So you can change the spacing between the different injectors. Here we are stuck with 16. It's already a big number because you have to duplicate each injector 16 times to get a full configuration. We have also pressure taps, which are here, which are connected to waveguide microphones. Like that, you can actually have the pressure in the chamber. And these are the injectors. They are all, in this case, premixed. This is the swirler detail. In this case, we had a swirler which was made of blades, profiled blades. And these are the flames that you produce. In this case, there was no, you see the injector was just a straight cylinder, but in practical systems, you have a cup. You have some sort of cup at the end of the injection device, And then we actually used cups, and you can find that the cup has a big effect on the flame. So the whole system is fed with pre-mixed air and propane. And you can put a camera on the side at a distance from this system, and using the microphones, you can see the pressure signals. And when we started working and scanning the whole domain, it didn't have instabilities. I mean, it had instabilities, but not the azimuthal ones. So for a while, we didn't know how to get these instabilities. And so by that time, we looked at the ignition, and it looked very interesting. So we started playing with ignition and thinking about how to get the instabilities in the meantime. And let me show you how this ignition takes place. So we ignite with a single spark. So you have a spark igniter. In engines, you have two sparks which are located on opposite diameters. So these are false colors. The flame doesn't look like that. It's blue, but like that, perhaps it's more visible. And so you see the flame propagates on the two sides, and then the two flames join. And so you have a delay for that. And this delay, this process is what is called light round. It's the circular ignition of this combustor. And afterwards, the combustion is established, and you have ignition. All this takes place in like 50 milliseconds. So it takes a little while to ignite. So in itself, it's a problem of interest to gas turbines. So we started to actually study this ignition. And one aspect which is important is to know if the effect of the bulk velocity. When you increase the bulk velocity, will it reduce or increase the delay? What do you think? You increase the injection velocity. Increase the delay. So who is for increase the delay? And who is for reduce the delay? Increase the delay. Well, it reduces the delay. Yeah. So let me show that. Yeah. It decreases the delay. So here you have two experiments. One done at 12 meters per second. Here 24. And you see we match the moment where ignition takes place of one of the injectors, and you see that this one goes faster than this one. So there is here a good problem that we studied experimentally, that we also studied using the G equation. In fact, let's see first that. Yeah, you see what we find from experiments is that the delay is diminished like that with a certain power of the velocity. As you increase the injection velocity, this delay is being reduced like that. And increase of the bulk velocity by 100% decreases the ignition delay by 23%. So the processes are like that. You have first this hot pocket, then you make an arch here, then you have flame front merging, and finally steady state is there. Yes? How do we ignite? We ignite using a spark. So now the spark is operating at a rate of 10 hertz. We deposit energy at a rate of 10 hertz. And for the equivalence ratios that we have here, essentially the first or second spark ignites the system.
In that point, in one point?
At one point. In practical systems, you have two spark igniters on the two sides. So But in this case, it was nicer to do it like that, to watch the process develop fully and not have the two flames and so on. Of course, we could do it. Actually, initially, we had 2 spark igniters just to imitate, to mimic what is found in industry. But then we took one out and we left. We also studied the effect of the position of the spark igniter on these delays and so on. So, in fact, there are some very nice simulations carried out by Boileau and all this group, especially the group of Thierry Poinceau. And they were really audacious because they started looking at the ignition in a real chamber. And you can see here the 2 flames. Actually, here ignition is obtained by 2 flames. And you have here the flame propagating in this complicated flow. And little by little, you ignite all the combustors. And finally, the whole system is being ignited. And actually, you can watch that with this film. This is a film produced by Mathieu Boileau and this group. And so you have, and the camera is moving with the flame. So you can see the flame propagating inside this combustion chamber and finally getting merging with the other flame, which was initiated by the other spark. So here, like that, they could cut the time for the calculation time by half because the 2 flames were propagating, one from the opposite spark, one from the spark, and it's a nice calculation that is published in this journal. And what we did was also to try to use the G equation in this case to propagate. This is a premix flame, and see if the G equation allows you to represent this process. And it's a special way of writing the G equation. You can actually modify that to place here the burn gas velocity and to place here a term which is very important, which is the ratio of the density in the fresh mixture divided by the density in the burnt mixture, which multiplies the displacement speed. So it's a different, you see, this is the standard G equation, but if you write it with respect to the burnt gases, you can actually exhibit this term, which is a term which you know accelerates a flame when it is when there is this is the volumetric expansion, which actually produces a flow which accelerates the flame. And by using the initial shape of the G of the flame, so you take that and then you use the you put this flame. This is what you find experimentally. These are the positions. I'm sorry, it doesn't come out very well here. And this is what you get numerically from this G equation applied. The initial surface is here. And then you propagate from this initial surface. And this is the full propagation. You start from here, and then the flame propagates in this direction, propagates in that direction. And so you can deduce, this is the experimental data, and this is the numerical values obtained from the G equation. So it doesn't mean that this tells all the problem, and you have to actually provide the velocity field and so on, and say something about the turbulent velocity. So, but you get something which is of the same type as what is found in experiments. So by that time, and the other thing is that once we had the data, we thought it would be nice now to use that data for numerical calculations, to do that using LES, because now this is a really challenging problem, because you not only calculate a steady state flame, you calculate something which is moving, and you have all these processes taking place, and how that is it possible to actually match or at least represent what is being measured. And this is the work of Maxime Philippe in our lab. And Mathieu Boileau actually joined us as a research engineer. And so we actually did the calculation. Now this is the million-hour calculation. It takes a million hours. It takes a century to have your result, but you use 6,000 processors. It's in a month, and you will see the video corresponding to that. So the point here is to be able to represent this process, especially the light round. This is a comparison between large eddy simulation and experiment. And of course, once you have a calculation, you can look at what drives the flame, what is the flow field, and so on. So this is the domain that is being calculated with the plenum, the injectors, all the 16 swirling injectors. In this case, we replaced the injectors by putting orifices so that it would be more, somewhat easier to mesh. And so we deposit a hot gas spherical volume of hot gases. We did 2 such calculations. So this is the initial kernel. And you see now the beginning. What is plotted is the isosurface of progress variable, and it is colored by the velocity. So these are flames which are now stabilized, and you have these flames which propagate and finally merge. It looks very realistic. And now it's compared with experiments. So what you see on the left here is the emission from the flame taken with a high-speed camera, and on the right it's the calculation. So it looks very close. You see even some of the features look alike, while this is a turbulent flow. So we get this initial expansion here. So when you look at the heat release, this is what happens. It increases, then it goes to this region here. Now the heat release, the flame are sitting here. They propagate, more heat release as we ignite the various burners. And then all the gases are burnt, and you go down to the steady state. Because initially you had fresh gases inside the combustor. All right, so that shows that we are able to, yeah.
So the turbulent flame speed in this model, is it constant or?
So now this was an LES calculation, so it doesn't rely on a turbulent velocity. You don't have to specify the turbulent velocity. You have a model. So in this case, it's the F-Tackle model that was developed in our lab, and that does. But we also did a comparison between 2 models. This is in the Proceedings of the Combustion Institute. We used the thickened flame model, essentially developed at CEFRC, and our model, which is tabulated chemistry LES model, and the 2 agree pretty well. Not quite, but there is a good agreement, and so this shows that definitely we come to a point where we can calculate such very complicated flows, swirling, ignition, transient. So and in addition, you can do actually 2 or 3 calculations with the number of hours that you are given. It's always a very competitive process, because we ask for hours a European organization. And of course, you compete with people doing biology, astrophysics, quantum electrodynamics, and so on. And they always consider that their topics are more important than yours. We are, and we are very modest. People, for example, in the climate change, they will spend hours and hours calculating a single realization, while we can do much more, but nevertheless, it's always a difficult aspect. So, for example, the first project was accepted, the second one, they decided that no. And so we had just a limited amount of hours. And for that amount, you cannot change your model or do something. You just hope that the model is perfect, that you validated that previously. You can do many experiments. In the meantime, we did a large number of experiments, but on the calculation side, there are two, and the two agree well. Yeah, the one at this velocity, the other one at another velocity. We were very happy with that. That's actually for the video we got the APS Milton Van Dyke Prize. It's a video that is available. You can watch that. So it was also interesting. In addition, I knew Milton Van Dyke well, so it's nice to have this award. Yeah. How many cells? 300 million cells. Yeah. Yeah, that's it takes an effort to do that, and it takes a team. It's not an easy job, but in fact, the thing at the beginning of the thesis of Maxime Philippe, we thought we would do it. At the end, we did it. So so he's done essentially 2 calculations. That's all. No, there is much more because first of all, you have to validate on single injector and so on, and you see if the profiles are fine, and you do a lot of work before you do these calculations. And then you do it very step by step. But then the large scale calculations you do only twice. So here you are, there is a risk. There is a risk not to be able to do it or to get a result like that, but it went well. Yes. It's the tabulation, the person who has developed this method is Benoît Fiorina in our lab, and with Nasser Darabia and other people, and we use their methodology and it's propane air. So I don't remember exactly which scheme was used, but this method is pretty good to deal with such problems. It doesn't deal with everything. It deals with such problems. All right. So now we spent enough time doing this ignition, and we had new ideas on how to make it more unstable. And one idea was to actually place, you see, the cups. So the injectors are terminated by a cup now. And why is it useful? It's because the cups, now the flames interact between themselves, and that helps. The other thing that we did was to place these matrix injectors. So you see this hole is for the pressure taps, and these are the matrix injectors. And so this one we call Mica 3, and this is Mica 2 because now we have these cups instead of just having a pure cylinder. It's closer actually to a practical situation. And we did model identification, more or less they give the right frequencies. And now what are the results? Well, there is a mode which is longitudinal, which comes in. This one is at low frequency because you see in this case, this is an open-ended configuration, and as a consequence, you have the quarter wave mode which is there, and it's at very low frequency here. you can see that all the microphone signals are in phase. This is the spectrum, the power spectral density. So you see a strong peak here and a harmonic right here. And this is how the pressure looks like. So basically, it's dominated by this mode. And what do the flames do? Well, most of the flames here are synchronized, but some of them execute the other motion. You see, they are blue here while everything is red. So this is the work of Jean-François Bourgoin. And here we are in a situation where it's essentially zero. And now we have a negative almost everywhere except at these places. And here we are in the middle at essentially zero fluctuation. And this is how the longitudinal mode looks like. So the plotting doesn't appear very well here, but basically what you see is that most of the flames have the same color at the same time. Not quite. So the whole thing is operating in the longitudinal mode case. This operates at this frequency. The images are obtained by phase averaging. So we use the clocking, the fact that we are synchronized to phase average. In fact, I told you that it is possible actually to have the combination of these two modes. You can have the spinning mode. So if you see, you can define a spin ratio, which is the absolute value of A minus the absolute value of B divided by the sum of these two values. And what you see here is that when S is equal to -1, it's B, which is not zero. And so this rotates in the clockwise direction. It's the negative theta direction. It's the clockwise. If S is equal to 0, A is equal to B, it's a standing mode. If S is equal to 1, it's a rotating mode, but it rotates in the counterclockwise direction. So the standing mode is like that, and these are two instants during the spinning mode. So the spinning is going like that, but you can have also situations in between. And the spin ratio tells you where you are. This was introduced in a different way by Stéphanie Évêque and Wolfgang Polifke and Pankiewicz in this paper, but their definition could not accommodate these various, it's a different definition. So our definition is this one. And how do you get this spin ratio once you have data? So, because what happens in this combustor is that it is a continuously switching between various possibilities. All the possibilities are there, and you don't just get the standing mode or the spinning mode, but you get something in between, and so you move from one case to the other. At certain instants during the oscillations, you have this sort of signals at the microphones. So here you have the microphones, and you see that all the microphones are synchronized like that. This is typical of a standing mode. You see, this is typical of the standing mode. In other cases, you have something which looks like a traveling wave, and it is indeed a traveling wave, and this is a spinning mode. You see, when you see your microphone signals like that, this is more like a spinning. So the signals themselves are the points, and what is in solid line is a reconstruction of these points, because you can use the pressure signals, you can use the knowledge that you have about the modes and actually obtain A and B. You can actually obtain A and B from the signals that you are recording at the various microphones. It takes in fact, it's a least square process which gives you A and B. And so it's possible to actually reconstruct And at every time, you can reconstruct A and B and say, what is the spin ratio? So this is a method to actually use the signals that you have and directly obtain the spin ratio. And this is the data, how it looks. So you do have, all the microphones have a large oscillation in pressure. This oscillation is around 800 hertz, which corresponds to the azimuthal, the first azimuthal, first longitudinal mode. And at some times during this, for example here, this corresponds to the spinning case. So in this region here, you are spinning. And in other cases, you are standing here. And then you can watch this spin ratio, and it takes a Gaussian shape. So basically, in most cases, you are around the standing mode, but you have cases where you are spinning and where you are spinning in the other direction. So this it switches from one mode to the other. It spins, sometimes it spins in one direction, sometimes it spins in the other, sometimes it's standing. Most of the time it's standing. It's slightly displaced with respect to zero. It's in one direction here. And the spin ratio varies as a function of time, and you can characterize that with the probability density function. It's close to a Gaussian. On average, the counterclockwise direction of rotation is favored. So how does the standing mode look like? Well, these are the microphone signals, and these are the heat release signals. So you see here, it's red, here it's blue, here it's essentially the same, and then you have blue and red here, and here again, you are red and blue, while here you have red and blue. So like that, you have the nodal line, which here is vertical. And this is how it looks. So it sloshes from one side to the other. You see, you have this motion which appears here. This is superposed on a turbulent process, so you need to do, in this case, we did DMD, the dynamic mode decomposition, to get this mode out, but you can do also phase averaging. It gives the same answer. And the rotating mode is like that. So you see that this red region is rotating around like this. You see it's rotating here, like that. And you have this traveling wave right here. And this is a calculation done by this group at CEFRC. You can see, and Wolf also here. The mode which is rotating is here. You have the positive is here, the negative is there, and these injectors respond to this mode. You see it rotates, so you find these in a real chamber. Now the chamber is not shown completely. It's just a cylinder inside this annular chamber, and these are the injectors that you have all around that. And you can also see that by looking at this is now unwrapped, and you see the injectors and what happens to the flames as this rotating mode is operating. You see the flames are dancing. They are moving sideways. And also the injectors respond to the pressure fluctuation. So there is a complicated motion of these flames. So this is the device of Jim Dawson and Nick Worth. They showed this data at the previous symposium. You see what I was saying is that the plenum has this funny shape here, and the injector has this central body, and because you have this central body, the actual velocity is augmented, and as a consequence, the swirl number is not very large. And also, the visibility of the flame is reduced, but they looked at from the top. They put a mirror and looked from the top, from the mirror, a 45-degree mirror, and so you can see how the flames move with respect to in terms of dynamics. So this is this paper. And now the injector tubes are pretty long here. That's also something which is unusual, and also they don't have any microphones here. So we have microphones. We could see the spin ratio. We can actually watch the flames fully. The diameter is also smaller here. It's 17. It's half our diameter. It's about half. And they use ethylene because ethylene has a larger burning velocity. So they didn't get any oscillations with the other fuels. So they turned to ethylene, and this allowed them to see some very nice patterns, rotating patterns, like here. You see that this pattern is rotating, and so that's in this paper. And you can change the spacing between the injectors, and they found that the spacing was important. That when the spacing is too small, then these oscillations are promoted. So in fact, the spacing has an effect because the flames interact, and this is so then it tells you that a single flame dynamics is not enough to represent things, but you have to have this collective effect, something where the flames interact. And getting back to our situation, I'm sorry, the film doesn't appear very well. You have blue and red, and here is the pressure fluctuation. And what you can see here is that the pressure is in phase. We look at one burner, and you see the oscillation in pressure. And you see that when the pressure in the chamber is positive, you have also positive fluctuation. So you are, in the case of the Rayleigh criterion, P prime, Q prime are in phase in this case. You have what we show here is actually the pressure distribution. What you see is only one or two, actually 3 injectors, but what we plot here is the pressure in the whole chamber, and what you can see is that this is what the pressure does, and you see that at the local injectors, the pressure and the injector fluctuations are in phase. And this is just what it tells again, all right? So perhaps a few questions before we stop for a second. Yes?
You showed a histogram about which way it tended to rotate.
Yes.
Have you tried switching the swirlers to see if it preferred the opposite direction?
No, we did not, because these swirlers, no, we haven't done that, no. But it is perhaps possible that this slight, that this displacement towards one direction is due to the general rotation that is, because all the squirrels rotate in the same direction. So they induce a large-scale motion inside this combustor, perhaps of not very large size. So this may be the reason why we have this slide. But the main result is that basically we are most of the time standing, but even you see this, it switches around. The case is not purely standing or purely spinning. It's moving sometimes here, sometimes there. That may not be a result, a fully universal result. It's what we get in this chamber. Perhaps if we have stronger instabilities, this might produce a purely standing mode or purely spinning. You will see in the next hour, I will then use the matrix burners. And in that case, we have standing modes, we have spinning modes, which are sitting there for a long time. And in addition, there is a case where you, depending on how you get there, you get either the standing or the spinning. So this is what we will see after the break. Yeah.
So you know that the pressure waves were used by the flame. When it hits the walls, come back again and then interact with another pressure wave comes from, another flame maybe. So how you recognize, or at least take this disturbance from the.
Yeah, so the question is, you have pressure waves which are emitted by all these flames, and the flames are actually the sources of sound inside this combustor. Now, all of that is reflected finally in the modes. The modes represent, it's a way to represent all these reflections, all the pressure waves. So it's a combination of modes, but basically, when you are close to the resonance, one mode comes out. So one mode represents actually the reflections on, you take into account the boundaries, all of that is here. So the time interactions between the waves are reflected in the modal structures. For example, you take this amphitheater, put a sound source here, at certain frequencies, you will find resonances. The people who have engineered this room have placed surfaces so that it would break all the modal possibilities and eliminate the resonances. But what you have, nevertheless, is you can find this, and this represents, in another way, this phenomenon of reverberation. Yes. Okay, so perhaps, yeah, last question then.
I just wanted to ask about identification of flame transfer functions or flame describing functions. Have you tried doing any nonlinear system identification?
So this, the question is more about the FDF. Is it possible to use a nonlinear identification of the transfer function using techniques that are used, for example, in controls? So the problem here is that you have turbulence. So if you use, for example, white noise or something which is broadband, and you have the turbulence there, then it's difficult to separate what is from turbulence and what is from what you send. Now, except in the linear case, you can use this cross-power spectral density and do that. So that can be used. That we've done that somewhat, but the energy is lower. Of course, you get immediately all the frequencies, but on the other hand, you have the problem of noise, of extracting from noise. So what we do more often is go frequency by frequency and get the transfer function. Now, the question also that is related to that is the flames interact between themselves. But if we want to get the FDF, we have to take a single flame and look at its dynamics. So we lose some of the interactive processes. So at this point, this is what we do at least. We take a single injector, place it on a different device, measure its describing function, and use that describing function to study the dynamics of this system. So there is still a lot to do to describe these interactions, the side interactions. That is not yet available.